Hello and welcome. This video is a presentation from a webinar hosted by satsearch on thruster technologies for small satellite missions. It's led by Armando Rojas from NanoAvionics, a small sat bus manufacturer and mission integrator that's currently based in 5 locations across the US, the UK and Lithuania. NanoAvionics is a participant in the satsearch membership program and has implemented more than 85 successful satellite missions and commercial projects in the past several years. This video discusses the company's smallsat thruster technology portfolio and experience. Hope you enjoy.
Hi, thank you, Narayan. So thank you for satsearch for organizing this webinar. I'll be walking you through the NanoAvionics EPSS. This is a development that we've done internally. So who are NanoAvionics? Who are we? We're a global prime provider of wide applicability end-to-end small satellite constellation technologies. And our main aim is to provide the market with an economic and viable range of small satellites for constellations and in general for other businesses that want to get into the space sector. Our philosophy is to pre-integrate these buses and satellites and pre-configure them. And in that, within that activity, we've developed our own propulsion system with some partners that are present here, for example, Bradford. The company is now based in Vilnius, Lithuania. That is where the headquarters are. We've now also got offices in Columbia, Illinois, and in Basingstoke, UK. We're over 100 strong now, and we've got AIT facilities in all of our various offices. So the EPSS propulsion system, enabling propulsion system for small satellites. It's a bit of a mouthful, so we decided to stick with EPSS. This is a blowdown type ammonium dinitramide ADN based green monopropellant system. We developed this system through various ESA projects, and the standard configuration carries a single propellant tank with a single thruster, and it provides about a Newton of thrust at the beginning of life. We've gone with a very modular design approach with this propulsion system. It is part of our design philosophy for all of our subsystems and platforms. So we chose to go this way in order to give flexibility to our customers with configurations. More than one thruster is available to our customers should they choose to have that configuration. The sizes go from 1.5 units to 3 units in volume, and the impulse can go from 1 to 4.5 kilonewton seconds. The wet mass is between 2 and 4.5 kilograms, and the delta V capabilities or the impulse capabilities can be adjusted based on your mission profile. So depending on what you want to do and how you want to do it, we will be able to tune those capabilities based on specific mission needs, but still maintain an average specific impulse of around 220 seconds. So that's more or less within the range that we have tested for, which is 214 seconds to 220 seconds. This propulsion system has flight heritage in several of our missions. Lithuanica Sat-2 and M6B are the most notable ones. We got successful flight heritage there, and we are going to be flying this propulsion system in multiple upcoming missions over the next 2 years. We have fully qualified this propulsion system using ECSS standards. This has allowed us to do a very extensive and successful qualification campaign, and we did multiple hot firing test runs for this system. It is pre-qualified and flight ready for a variety of mission profiles. We'll go into that a little bit later. And our partners we know that our partners have tested the thruster itself to more than 45,000 pulses at thruster level, and we've tested it to about 1,000 pulses at system level. So what kind of mission profiles? The short answer is anything that requires a thruster. As we know, most of the market is going to be needing thrusters more and more, regardless of size. So we have designed it where you can either look at formation flight for constellation deployment, track compensation and orbit maintenance, orbital maneuvering, synchronization and positioning of communications equipment and payload instruments, obviously end-of-life purposes and deorbiting, and propulsion component development and production. So if you're doing a very specific mission that requires custom-made propulsion systems and custom-made configurations, we can also kind of develop that and make sure that you can create a spacecraft that can help other spacecraft move around. We can also help in full system development and production for custom developments. In general, this thruster, in terms of in-orbit operations, can be used with the payload on, but this will depend entirely on your power budget and the size of the satellite. It all kind of revolves around the duty cycle, but yes, it can be fired with a payload on. How to use it? Well, we have implemented a very simplified and flexible approach to this. The user sequences through different system states by using commands only available in a particular system state, and this ensures the system is not operated in any improper way. Also, the system is protected by multiple layers of safety features, whereby the system will continuously monitor the health of the propulsion system and inhibit activation of any of the actuators of the system should there be a case where non-nominal values are detected. So how have we done how do we do the assembly, integration, and testing, and the quality assurance of this thruster? Well, we do a lot of component level testing. Each individual hydraulic component is individually accepted for functionality and leak tightness after assembly. So we will ensure that all of these components have no faults and it will be operational. Each individual thruster is also separately hot fired in order to measure its performance by our partners at Bedford. Each propellant tank is pressure tested and inspected via non-destructive inspection to ensure that there are no leaks to that pressure tank. All of the accepted components are then integrated as a system. Each hydraulic joint is verified for leak tightness, this includes welds or elastomer seals. Then we do a full propulsion acceptance test campaign with appropriate mission-specific environmental loads. So this includes the functional testing, making sure all of the electrical interfaces work. We do pressure testing, we also do vibration testing, and we do thermal vacuum testing. The thermal vacuum testing is something that we have managed to develop within our own premises. We did a couple of hot firing test runs. On the right side, you see the thruster firing up. It's quite a cool image in my opinion. This is a run that we managed to do where we got a single continuous pulse for more than 15 minutes, while also maintaining 1 Newton of stable thrust. The single sessions that we've done end up having a cumulative time of over 44 minutes of firing, and that includes the over 1,000 pulses. Usually, we've noticed that chemical propulsion testing capabilities are limited in Europe, and the pandemic kind of forced us to kind of look at other solutions. So we built and used our own testing facility for covering this sort of testing need and any future needs that we may have, which is quite cool. We've got extensive experience as a company in dealing with propulsion systems, chemical and electrical. We've actually also worked with Exotrail and with Propulsion before, so we are very comfortable in integrating this sort of propulsion system, whether our own or another partners. We have multiple past missions that have had propulsion systems on them, as well as many upcoming missions. As I think we've mentioned, there's been a general theme throughout. There's more and more missions that are going to require this sort of systems on board. We effectively managed to demonstrate the green monopropellant in the Tuanica Sat-2, and in M6B we also demonstrated the mission control side of things and propulsion control side of things quite successfully. Future missions will include our larger systems, the C2 and the C3 configurations. We follow EPSS standards as well as any mission-specific requirements. So we work under slightly modified EPSS to better suit our needs, but we try to not modify that standard too much so that we're compliant with that standard all the time. There's also some product-specific requirements that have been derived from all this testing and staying to the standard that have allowed us to kind of get a very, very nice custom-made process under that standard. Here we have some performance metrics. On the left side, you've got the propellant tank pressure versus the propellant consumed. The propellant consumed would be the x-axis and y-axis propellant tank pressure. As we consume propellant, the tank pressure will drop, as you can see. And the graph on the right is steady state vacuum thrust versus propellant tank pressure being the x-axis and thrust being the y-axis. Now, this is a counterintuitive chart. We are going to start at a higher pressure, and then we're going to move to a lower pressure. So what we do notice is that at the beginning, as you can see at the beginning of life, the thrust is around 1.1 newtons, and it will go down as we lose pressure in the tank by expending some propellant. The next graphs show steady state specific impulse versus propellant tank pressure. So as you can see, that indicates us the range of specific impulse that we can get. But the important graph that I'd like to focus on is the graph on the right, where we can see the average specific impulse on the y-axis and the pulse length on the x-axis. What this graph shows is that if we do short pulses, we will get a lower specific impulse, and if we get longer pulses, we get a higher specific impulse. This allows us to work with the customer and adapt to your mission parameters and mission profiles based on what you may need to find that optimal kind of pulse length based on the level of efficiency you need, or the level of the length of pulses you may need during your mission. How do we integrate our thruster into our spacecraft? Well, our requirements specifically for this thruster would be an ISO class 8 room, clean room or better. We can be present for the integration to help out our customers integrate into their platforms. We should also note that we've gone for a very kind of easy to integrate design. It's pretty straightforward. We just use some screws on the interfaces here, and then we just bolt it onto the platform with a relevant thermal surfaces in the right place. It's more or less 20 to 24 screws. We also require a little bit of kind of thermal, let's say, savvy. We need to understand your thermal conductance and operating temperature requirements, and we will also need to kind of see how your thrust to heat radiation would affect your platform during firing. This needs to be considered, and the thermal requirements are, as well as the thermal interface instructions, have to be kept below 40 degrees Celsius during system operation. And we also need to consider the plume, which is basically the exhaust around the nozzle. And if it's placed next to certain components, there has to be a little bit of analysis done in order to determine what the thermal loads are, or if there's going to be any potential contamination to any sort of sensitive material you may have next to the thruster. In terms of training, we can provide training to all of our customers. We will actually train you in loading procedures, hot firing sequences, and general system operation. As I mentioned, we can also be present during integration. And I was going to say, let's have a Q&A, but we'll have a Q&A right after. So thank you for listening. My email for any questions you may have that we can't cover during this webinar due to time constraints is just there. It's armando@nanoavionics.com. Thank you very much for listening to our presentation.
So there we have it. I hope you enjoyed this short video about smallsat thrusters and how they're used in space missions today. Now, to find out more about NanoAvionics, please go to satsearch.com and search the platform for information on the company's products and services. Also, let us know if you've got any questions or comments or requests for further information. And thanks again for watching.